Welcome to our presentation on how multiple agencies collaborated to battle congestion in New York City. My name is Victor Darius from Global Traffic Technologies, the manufacturer of Opticom Priority Control Systems, and joining me is Mark Yedlin from Greenman Peterson Consulting Engineering Firm. We'll be covering how the busy streets of New York was affecting the travel time of New York City Transit, how the challenge was overcome by creating a collaborative solution, the results, and future implementations. Here's some of the challenges and complexity New York City and the partners involved had to overcome. New York City Transit do 2.3 million bus trips daily. They have 5,700 buses operating on 2,800 miles of bus routes. The public transit system is operated and managed by MTA New York City Transit. The streets and 13,000 signalized intersections are operated and managed by New York City DOT. As you can appreciate, there's a lot of traffic going through it. Bus travel speed have declined from 9.1 miles per hour in 1996 to 8.1 miles per hour in 2006, making New York City the slowest buses in the United States due to congestion. Urban challenges New York has to work with. It has to address dense congestion corridors, heavy pedestrian traffic, including a large proportion of slower elderly pedestrians, substantial number of double-parked delivery trucks, urban canyon environment inhibits GPS signals, the need to maintain signal coordination, different communication standards and security across various networks, and multiple agencies with different schedules, procurement process, budget constraint, and staffing limitations. Multiple stakeholders had to collaborate together to develop a transit signal priority solution that met some of MTA New York City Transit requirements by leveraging existing infrastructures, managed and operated by New York City DOT, leverage some of the existing technologies inside the buses, as well as meet MTA ridership experience. One of the complexity we had to overcome besides technology was budget and who reports to whom, and ensure the communication channel between all the parties was defined and open. The stakeholders are MTA contracted GTT from the Transit Signal Priority, New York City DOT contracted GPI the engineering firm, and Transco as ATMS provider. The proposed and deployed solution since 2013 is a centralized TSP architecture. GTT developed a software module that resides on the existing vehicle computers and a back-office software to provide an interface between the vehicles and ATMS. Our platform provides the flexibility to leverage the existing GPS in the bus, the vehicle-to-infrastructure communication network, and existing vehicle computer hardware. How it works is, as the vehicle approaches the intersections, it sends a check-in, check-out request to the centralized server located at the MTA, and then sends a request to the ATMS. No additional hardware from GTT is required at the intersections. Otherwise, if New York had to deploy and install additional hardware at 13,000 signals, it would take over 5 years to deploy and configure. Our platform developed in New York is for the present to the future. As you can see from the vehicle, we're agnostic from the communication and hardware. On the server side, it's a platform being located, and at the intersection we have no equipment. We rely on the performance and the partnership of the ATMS and the DOT. From the communication backbone, we're completely communication agnostic. We work on radio base, cell base, fiber, etc. Now Mark Yedlin will share engineering processes to optimize the TSP implementation.
Thank you, Victor. I'm going to tell you about the important traffic engineering decisions that are required not only for New York City, but any place where transit signal priority is to be implemented, and how these decisions are made and the results of these decisions play a paramount role in the actual performance of the TSP system. So these are actually critical implementation decisions wherever you install TSP. For example, what is the foundational background signal timings for which we will then overlay TSP actions? If we can come up with productive signal timings, then we can maximize the effectiveness of TSP. And this can, in fact, sometimes double and even triple the benefits of TSP alone if we provide a sound foundation in the background timings. The next question that has to be answered in any implementation is which intersections along a corridor are we going to be equipping for TSP? And, in fact, should we allow buses to receive TSP in both directions at that intersection, or perhaps only in one direction? At each of the intersections where we deem it relevant to include TSP, what are the signal phases that we should be adjusting? What are we extending? Which phase are we truncating? The next very significant question is how much time do we actually have at the traffic signal to be able to extend or truncate phases so that we can expedite buses, but at the same time come up with an acceptable level of potential disbenefits to the cross streets? What's the best that we can do in that regard? The next critical question is, when do we actually start to adjust a traffic signal for the presence of a bus? How far should the bus be from the intersection before we actually start to change the signal timing? If, in fact, we start to change the timing too soon, we may be calling for an extension and the bus will not be able to take advantage of that if it's too far away when we start that action. When we have buses approaching an intersection from perpendicular directions, those are calling for competing phases, then the question becomes, which call should we handle now? How do we reconcile these competing calls? And then, of course, every agency wants to know, what is the result? How much time can we actually save for buses? And what's happening to cross-street traffic? And if we know that, we can then make the decision as to whether the investment is worth it. The fact of the matter is that the answer of what the benefits will be is totally dependent upon how we answer all of the questions from the top of the page down until the last bullet. So the fact of the matter is that we don't just have to answer these questions once. We have to answer them multiple times. In fact, all of these questions have answers that vary by the time of day. Traffic volumes are different in the morning than in the middle of the day and in the afternoon. The signal timing plans are different by time of day. So all of these answers dependent on time of day. And the question about when to act actually varies by direction. At any given intersection, you can have two buses approaching from opposite directions, but if one direction is moving faster than the other, then when you would actually want to respond to that bus would be different based on the direction. So all of these questions have to be answered multiple times. And given the complexity, since we are looking at corridors and the number of questions that have to be resolved, it turns out that traffic simulation analysis is an essential tool to be able to evaluate the answers to these questions. And in fact, we can iterate our analysis, varying these answers and coming up with the best solution that will provide the most benefits to buses with the least effects on any cross-street traffic. So this methodology was applied for New York City on their first corridor, where they used the system that Victor described. And this corridor is in Lower Manhattan, starting at the Staten Island Ferry Terminal at the southern tip of Manhattan. It extends up for 2.2 miles, has 34 signalized intersections. This is an intermodal corridor since the corridor ends and begins in the south at the ferry terminal. And this particular corridor is the second busiest corridor in New York City. So there's a saying, if you know the song from Frank Sinatra, New York, New York, if you can make it there, you can make it anywhere. Well, within New York, if you can make it on this corridor, then you can make TSP work on any corridor. So this is a particularly challenging corridor. Here's how we do it. We actually build computer simulation models replicating the algorithms that the city and the MTA plan to use for TSP. Notice on the top, we're following a bus without the system, and on the bottom, we're following the same bus with TSP. Notice that on the bottom, that bus has been able to move ahead because the TSP system kicked in, and that bus received an early return to green. It's happening here again at the fourth intersection. And we can see on the bottom, we are keeping tabs on how much time the bus has saved so far as a result of the TSP system. The little specks that you can see in the crosswalk, those are actually the pedestrians, and we've counted all of them, and we are accounting for all of them in the model. Periodically, as is going on now, you can see bicycles as well. We're following the bus, and notice that the actual travel time savings varies. It's not linear. It bounces around depending upon the conditions. So right now we're at 2 minutes and 53 seconds of savings, and that just changed. We're 5 intersections ahead, now 6 with TSP. Now this is an interesting situation because a bus is now servicing passengers at a station. And as is typical, notice that the traffic signal is green. But as far as that bus is concerned, that green is being wasted because the bus is still servicing passengers. And as is typical, now that the bus is ready to move, the signal is red. But if you look to the right, you'll see the system's responding with an early return to green. And in fact, the bus is moving out and is not delayed as much as it would have been otherwise. So now we're turning down towards the Wall Street financial district, which is where this is. And notice there was a red rectangle there. That was a double parked vehicle. We're taking into account all the dynamics of this very tumultuous traffic environment. All the pedestrians, all the bicycles, all the double parked trucks, taxis, etc. Another important element here is that there are a fair number of seniors, and they require more time to cross the street, and that gives us less time to be able to offer 2 buses with TSP. So now we're heading down towards the Staten Island Ferry Terminal. Notice there's a particularly large number of pedestrians here. Again, there's a red rectangle. Vehicles are stuck in the rightmost lane because of a double parked truck loading or unloading. And the system is kicking in and trying its best to churn out the traffic and get it through the intersection. Nevertheless, there's only so much that any TSP system can accomplish. And notice it repeatedly called for the green and brought the green back early, in this case twice, in order to help that bus. And that's how this system operates. And at the end of the day, we actually are able to get savings of over 3 minutes. Right now we're down to just under 2 minutes. Notice as we keep going, we're picking up more and more savings. We're now over 3 minutes. and we're coming right near the end of this corridor. And because of the delays at this intersection, because of the congestion, this savings will drop a little bit as we move forward. And this is the last intersection. So our savings are just over 3 minutes. Now, if you are a passenger on this bus and you're heading to the Staten Island Ferry Terminal to catch a ferry, that 3 minutes and 14 seconds here of savings is very significant to you. So we can learn a lot by looking at these displays, including determining whether it makes sense to provide TSP in both directions at an intersection. We have decided through looking at these displays that in some instances the TSP helps the bus in one direction, but actually because there was a very good progression underlying to begin with, the TSP is actually interfering with that momentarily at that location, and it makes more sense not to provide TSP in that direction at that time. So there's much that we learn from this type of display. At the conclusion of this analysis, this TSP system was successfully implemented, and in fact we saw travel time savings in the morning of up to 18.4% reduction in travel time. That's very significant. Not only did we help the buses on that corridor, but we had an unexpected benefit as well because of that foundational signal timing that we talked about at the outset. We were able to actually come up with signal timings that made this system a success both on the corridor for buses and for the cross streets. It was a win-win. Cross-street delay also was reduced, and you can see the percentages here. Besides the travel time savings, if we look to the right, you'll see a chart that shows us that the variability in travel times from one bus run to the next was reduced as a result of this system. That made the system more reliable and is something that passengers particularly appreciate if there's more regularity in how the buses are performing. As a result of the success of this system in Lower Manhattan, you can now see that the City of New York is implementing this on a total of 14 major bus corridors, over 650 intersections and 71 miles of roadway. This work is all in progress now. 6 of the corridors will be completed by the end of 2017, and the remaining corridors will be completed by 2020. And there are additional corridors that are in the drawing board now, and work will begin on those subsequently. So, to sum this up, the collaboration between the City of New York, Department of Transportation, and the MTA, its transit agency, was able to provide a substantial set of benefits for transit operations in New York. And through proper hardware in the GTT technology and through proper engineering and simulation, as was demonstrated here, we're able to fine-tune the performance of the TSP system to ensure optimal success. And the solutions that are demonstrated here are available to be implemented anywhere else. Thank you very much for participating with us in this webinar. And if, in fact, you have any questions, please feel free to reach out to Victor or to me at the email addresses shown here. Thank you very much.